Okay, I'm going to go through some work and power problems. We did these in class, but I figured it couldn't hurt to go through them in case you didn't do them or you weren't there or you wanted another review. Okay. Um, so, first are some examples of when we do or do not have work. Remember, with work, your force and your distance have to be in the same direction. Otherwise, you're not doing work. Also, you have to move something a distance in order to do work. So, the first example, this guy carries a cat across the street. Carrying is not work because your force, okay, so like if you're carrying something, your force is going to be like an upwards force because you're really overcoming the force of gravity of the object. But then if you're walking, say, this way, okay, those are not in the same direction. They're actually perpendicular to each other. So carrying something is never going to be work, which seems weird, but that's the way it is. Ben pushes a wheelbarrow up a hill. That would be work. Jan throws a ball into the air, and it says before she releases the ball is work done. This one's a little tricky. I said no because I thought she's just holding the ball, so it's not moving yet. You could say that she's holding the ball up and exerting a force on it and picking it up, but I don't know. That one's kind of strange. But Diane kicks a soccer ball, overcoming a force of friction. Yes, that would be work. Steve raises a car using a force. Yes, that would be work. In that case, he's raising the car using a pulley system. So his force would be in this direction, but then his distance would also be in the same direction. He's raising it using like a pulley, and so it's going up. Joyce pushes against a block, but it doesn't move. No work there because it's not moving. So generally, if you're not moving something, it's not work. If it's like this, where your force and your distance are perpendicular to each other or not in the same direction, then it's not work. This one, pushing the wheelbarrow up the hill, he's pushing at a force that's at an angle. He's also moving it at an angle up a hill, so they would be in the same direction. So, okay, so just a few examples there, and then here's a few problems. I'm just going to talk through them really quickly. Remember, the equation for work is force times distance, and then power is just work divided by time. Power is just our rate at which we do work. So once we've calculated work, power is really simple. You're just dividing by time. So first example, a wagon's being pulled with a 50 Newton horizontal force and it's moved 8 meters. How much work did she do? This one's really straightforward. We're just going to multiply the force by the distance. We get 400 joules. Remember, joules is our unit for work. Another straightforward one, Abby pushes a crate. They give us the mass of both of these, but we don't actually need it in these cases. She pushes it with an 80 Newton force and moves it 14 meters. How much work did she do? So we just multiply force by distance, get this number. Dan lifts an object vertically. How much work did he do? When we're lifting, we're basically, our force is this, our force of gravity, because you're overcoming the force of gravity of something to pick it up. So when you calculate the force part for lifting, you're going to multiply mass by G, same old 9.8, and then that's your force. That's the force part of the force times distance, and then multiply that by the distance it was lifted. So here it was lifted up 3 meters. So we multiply all that out and we get 441. Similar here, a person weighing 630 newtons climbs up a ladder. Now they've already done the M times G here for us because we see that this is in newtons. So this is already the person's weight or force of gravity. And we can multiply that by the ladder that they climbed. This one was kind of like the one y'all did yesterday with the step ladder when we did our stations. Okay, and then we got a few power examples. So what's the power of a kitchen blender? It performs 3,750 joules of work in 15 seconds. We're just dividing work by time to get power. Power is in watts. How much work is done using a 60-watt light bulb for 3,600 seconds? So this next couple, we're using the power equation and rearranging it. So this is another one of these triangle type, I guess. Power equals work times time. So if you need to get work, in this case, they want to know the work, we're going to look at work equals power divided by time. Actually, I did that wrong. Never mind. You can't really use the triangle that way. Let's just look at the equation. So power equals work over time. If I want to solve this for work, I'm going to have to multiply both sides by time. So I end up with work equals power times time, which is what I've done here. Power, 60 watts, times time, 3,600 seconds, gives us this much work that's done by the light bulb. And then this one we're solving for time. So again, let's go back to the power equation. Power equals work divided by time. If you're going to solve for time, then we're going to have to, we're really going to flip-flop these two. So we're going to have time equals work divided by power instead. And that requires like multiplying by something on each side and dividing by something on each side. But also a faster way to look at it is flip-flopping these two variables. Okay. So time is work over power. Here's my work. Here's my power. I get 8.3 seconds. And then how much power does it take a person with a weight of 600 newtons to walk up 15 meters of stairs in 12 seconds? This, again, is somebody overcoming their force of gravity, going up. They're like lifting themselves. You could think of it as they're going up the stairs. So this is their weight. This is the force. We're going to multiply that by the distance they walked. 15 meters, so that gives us our work, and then we're going to divide that by time, and so we end up with 750 watts. So anyway, so that is a few different examples of work and power problems.